Hi. In the previous video, we've seen how to compute the cardinal spline. And the cardinal spline was an interpolation spline that was going through every data point. But we've noticed that at best, we could have only a C1 continuity and we couldn't have a C2 continuity. What we will study today is the Uniform Cubic B-Spline, which is an approximation curve because we won't go through the data points. But at this time, it will actually give us a C2 continuity. So we'll see how to compute a uniform cubic B-spline using the de Boer algorithm. And the de Boer algorithm is fairly simple to use. The stuff that you have to do is, if you have a bunch of points and you want to fit a curve through it, the first step is to split every edge in 3. So you have equidistant points now on those lines. And now that we have those, we could actually start to connect the last and the first one, and then the last and the first, the last and the first, and so on and so on. And once you've done this, we could start to split each of those new edges in half. So you have a point in the middle now every time. Now that we have those points, what we could do is to use those 4 points we have here and give them inside of a Bezier curve, saying that that's a cubic Bezier curve we want to build here, and then we can give the next 4 points to the next cubic Bezier curve, and that's how you actually build a uniform cubic B-spline. Now it has the advantage that it has computed for us those tangents, make sure that the points on each side were equidistant and on the same line. So actually, we've done all the stuff that we said that was annoying to do on the Bezier curve when we stick them back to back. And by doing so in this way and making sure that we have the points in the proper place, what happened is that we have a C2 continuity. So if I redraw this exact same curve here, you could see now that my first derivative is continuous, and my second derivative is also continuous. So I have continuity in C1, C0, C1, and C2. Now, the same way we've computed the cardinal spline using Hermite curves, and then we decided to try to find the mathematics to be able to compute directly cardinal spline without the need of going through Hermite curves. We could do the same for uniform cubic spline. Instead of having functions that will give us all the points that we have to give to Bezier curves to compute those, we can actually find a formula that will allow us to directly compute a uniform cubic B-spline. And this algorithm is the Cox-de Boer basis. It's a bit like going from the Bezier curve using the Castelgio algorithm to the Bernstein basis. Now we're going from the de Boer algorithm to the Cox-de Boer basis. And how it works is an iterative process to build those bases. And it's a bit tricky to understand. Maybe if I just show you the mathematics. It's an iterative function that starts with the simplest step, and then I will show you here mathematically. So the way the Cox-de Boer basis starts, it says that it has a bunch of knots. So that's your points you want to have. And in this case, because I'm using the cubic version, what I want to have is basically 4 knots, meaning that I have 5 points, let's say. And what happened is I have a points at 0, at 1, 2, 3, and 4, for instance. And that gives me 4 different curves. And the curves see, and they're just on and off. And that's what the definition is here. It says that if I have a basis of degree 0 for index I, it says the value is 1 if my t value, that goes between, in this case, 0 to 5, or 0 to 4, sorry. If my t value is bigger than the knots before and smaller than the knot after, actually I'm 1, otherwise I'm 0. And that's what you could see here. I have my first base, which is the blue line is 1 and a drop at zeros, and then I get the yellow, and then I get the green, and then I get the red. So I get 4 different curves that just on and off. And then if you want to start to compute a higher degree, it's an iterative recursive function. So basically it says that you take the level, the base before and with the index I plus 1, and you do basically a linear interpolation, which is a bit more complex now because we have range and all that kind of stuff, but that's what those 2 functions here are doing. They do linear interpolation between the different bases. And so meaning that we started from the 4 different bases. Now we have 3 bases, so that blue triangle is the interpolation between the blue square and the yellow square. The yellow triangle is the yellow and green, and the green triangle is the green and red. And then you can go one higher step, and then you can interpolate between the 2 triangles, which give you that nice curves. And then you can interpolate between the 2 curves, and that you get 1 big curve. And that gives me my final answer. That's the curve I'm interested in to try to compute my uniform cubic B-spline. Bit abstract at this point still. So what I will do is that I will redo exactly the same mathematics as the one I've done here, except that this time I will do them symbolically, so I can compute them and see the mathematics behind that nice curve I have here. And so this is exactly the same formula I've computed, except that I've solved it and asked it to collect for my different points, my different base, basically. So I get base 1, base 2, base 3. And that's the formula for this curve, right? So again, you can see it's my first base multiplied by a bunch of t's and all that kind of stuff, as we've had the habit to see most of the time. And if I turn them in 4 different bases, so I really have my first base here, the function is the t cubed divided by 6. So I get t cubed divided by 6. Give them 4 different functions, and I give them the proper range. You see, I have the curve as we have here, except that now I have colored them in the 4 different pieces I had. So I have a piece between 0 and 1, and 1, 2, 2, 3, 3, and 4. But that gives me that nice curve. And so now that I have this, basically what I want to do is, instead of having that nice curve that goes between 0 and 4, I want to bring that back between 0 and 1. And I basically don't want to squish the curve itself. What I want to do is I want to slide each piece of them to bring them back to between 0 and 1. So I have my blue between 0 and 1. I want to move the yellow between 0 and 1, the green between 0 and 1, and the red between 0 and 1. And that's what I do here. I take the function I had upstairs, except that I'm substituting t with t plus 1, t plus 2, t plus 4 to slide them. And that's the different functions you will have now. So t cubed hasn't moved. So my first one hasn't moved. The other one is a bit different than before. And what happened is that if I use this as the 4 different functions now, we could see that I have what I wanted. I basically have the 4 bases right on top of each other between 0 and 1. And it's basically as the one we had with the Bernstein basis. I mean, the sum of all of those curves is always equal to 1, no matter where we are between 0 and 1. That's the advantage of those bases. So it's a basis the same way within the Bernstein basis, it's just different shape. So that will allow us to do a bit of different things. So what we could do is that we could use those 4 different bases and multiply them by the different points we wanted to use. So you have point 0, point 1, point 2, and point 3. The 4 different points will be multiplied by the 4 different bases, basically the same way we did the Bezier curve. And so what we do is we take the one we shifted the most on the left. So basically the 0.3 is my first base, then 0.2 is my second, 0.1 is my third, and 0.0 is my fourth. And I can turn this into a matrix form as I usually do. So what we have is all my mathematics into the matrix form. I've just put the divided by 6 here in front because it's basically everything is divided by 6 all the time. And so that's the B-spline segment now. It's just a matrix form again, and just the multiplication of one matrix. And I can compute a B-spline by just moving back to back a bunch of points. And then we could see that if I render this again directly, I have now the same curve that I had before, except that I'm not doing the split linear computing, all that kind of stuff, giving that to the basic curve. I'm just directly using my matrix to generate this. And the same way we've done with the cardinal spline, you know, if we wanted to actually start at the first point and that kind of stuff, if we want to do the same, basically we actually have now to repeat it 2 times. So you have to put the first point 3 times and the last point 3 times. And if you do this, you have a curve that starts at 0.0 and end at 0.1. And so this is how you compute the uniform cubic B-spline. And that will be the last type of spline we will study in these videos, because I have most of what we probably encounter when we do animations. If later we need to go through a different type of curves, because there is still other curves, other splines, we will see if we need to make a new video. But for now, that will be the last type of curve we want to see. And in the next video, what we will see is how we could use those curves to actually encode animation data. See you next time.